Hello everyone, welcome to this lecture series. Today we are going to talk about limit involving infinity and asymptotes of graphs. When we say limit involving infinity, then we can talk about two particular cases here. That one is when the limit value is finite, but the domain x values uh, goes becomes large in magnitudes. That means x tends to plus infinity or x tends to minus infinity. The second possibility is that the x values are finite but the corresponding limit value becomes infinite. So for any x tending to point C, the function values becomes too large in magnitude. Okay, so we'll take the first case when we have finite limits as x grows too large in the positive direction or in the negative direction. That means x goes to plus infinity or x goes to minus infinity. Okay, so first we'll take about definition. When x goes to plus infinity, we say that fx has the limit L as x approaches infinity, and write limit x tends to infinity of function equal to L if for every epsilon positive there exists a corresponding number m such that for all x such that for all x which are greater than m implies that the function distance from L is less than epsilon. So here this limit on function when x moves increasingly far from origin in the positive direction, because x becomes too large and goes towards plus infinity, the function value takes on L. That means we say that for every possible epsilon positive we have a corresponding m such that you choose any x which is greater than m. Okay, so we can find a positive number m such that for every x which is greater than m, the distance of function from L is less than epsilon. Okay, so for every epsilon you can find a correspondingly one number such that you choose any x to the right of that number, and on every such x the function distance from L is less than this epsilon. Okay, so if it is true, then we say that the limit of the function when x grows large is L. Okay, similarly we take that when x goes to minus infinity. Okay, so x goes to becomes large but in the negative direction. Okay, then we say that the function fx has the limit L as x approaches minus infinity, and write that the limit of function as x goes to minus infinity is L if for every epsilon positive there is a corresponding number n such that for every x smaller than this number. Okay, so for every x which is towards the minus infinity, the distance of function from L is less than epsilon. Okay, so that means function lies within the epsilon distance from L whenever x is for every x number smaller than this n number. Okay, so these two are the definitions for finite limits when x goes to plus infinity or minus infinity. And with this definition, all the limit laws which are true for limit x tends to C for finite limit value, those limit laws also hold here for limit x tends to plus infinity or limit x tends to minus infinity. So those laws were like sum rule, difference rule, product rule, and so on. Okay, so those all rules hold for plus infinity as well as minus infinity. So I take one example here first, that show that the limit x tends to plus infinity on 1 by x is 0, and the limit x tends to minus infinity on 1 by x is 0. So to prove this first result, let epsilon positive be given, and so we must find a number m such that for all x greater than m, the distance of 1 by x from 0 is less than epsilon. Okay, so this holds. And if you solve this, we know how to solve using formal definition. We did it now in the previous lectures also, that we solve the epsilon inequality first and then try to find out this number based on epsilon. Okay, so we solve this first. Okay, so modulus of 1 by x is less than epsilon, so immediately we have that 1 by x less than epsilon, so x will be greater than 1 by epsilon. Okay, and if you compare this, then I can say that if I choose m to be 1 by epsilon, then uh, if m I choose to be 1 by epsilon or any larger positive number, then these two conditions will hold simultaneously, that we will have our result that limit x tends to infinity 1 by x will be 0. Okay, so if you look at here, then if I choose m to be 1 by epsilon, okay, so for every epsilon, if I choose m to be 1 by epsilon, then for every x which lies to the right of m, okay, for every x greater than m, okay, so for every x which lies here to the right of m, okay, the distance of this function from the 0 is less than the epsilon distance. Okay, because this curve will move and it will get closer and closer to 0. Okay, so so it is also written that no matter what positive epsilon is, the graph enters this band at 1 by epsilon and stays there. Okay, so that means the function distance, that 1 by x distance from origin, is always less than epsilon. Okay, for all x greater than 1 by epsilon. Okay, so both these conditions are simultaneously satisfied, and we can say that limit x tends to the infinity 1 by x must be 0. Okay. Similar is the second case, but in this case, instead of moving to plus infinity, you want to move to negative of infinity. Okay, so for in this case, we have to prove that for every epsilon positive, we must find a number n such that for every x which is less than n, implies that the distance of 1 by x, distance of function from origin, must be less than epsilon. Okay, and because we are moving to the negative direction, so we can use the if we open this inequality, then it is minus epsilon less than 1 by x less than epsilon. Okay, so this 1 by x less than epsilon we used here because we are moving to plus infinity. Okay, so if we are moving to the left hand side, then I will use the inequality that minus epsilon is less than 1 by x, and that will immediately give me that x will be less than minus 1 by epsilon. Okay, so if I compare these two, then I can choose n to be minus 1 by epsilon or any smaller number than this. Okay, so both these will hold simultaneously if I choose n to be minus 1 by epsilon or any number less than this. Okay, and both these will satisfy, so immediately I have this result that limit x tends to minus infinity on 1 by x must be 0. Okay, so 1 by x graph on the left hand side is this. Okay, so for any x less than minus 1 by epsilon, okay, so for all x values here which are smaller than this minus 1 by epsilon, okay, the function distance from origin is less than the epsilon distance. Okay, so that's what this second result is. So both are simultaneously satisfied, and we have that this limit definition holds. Okay, now the important uh, thing that we can calculate from here are asymptotes, and when x grows large to plus infinity or minus infinity, then we can calculate horizontal asymptotes, and horizontal asymptotes are straight lines parallel to x-axis, so you can represent those line by the equation y is equal to b. Okay, and so a line y is equal to b is a horizontal asymptote of the graph of a function y is equal to fx if either this holds or this holds. Okay, so this is that the limit of the function when x grows to plus infinity is b. Okay, and the second statement is that the limit of the function when x grows to negative infinity is b. Okay, so if the limit at plus infinity or the limit at minus infinity is b, then y is equal to b is the horizontal asymptote on that end. Okay, so if this holds, then y is equal to b is a horizontal asymptote at the plus infinity side, and if this is this holds at minus infinity, then y is equal to b is a horizontal asymptote at the minus infinity side. Okay, and it may happen that both hold, so this y is equal to b will be horizontal asymptotes at both ends. Okay, say for example, if we have to find the horizontal asymptotes of the graph of this function, which is x cube minus 2 by modulus x cube plus 1, then to calculate horizontal asymptotes we just need to check what happens when x goes to plus infinity and what happens when x goes to minus infinity on this function. Okay, so we need to calculate the limits as x grows too large to plus side or minus side, and because this is a rational function, and if we have to calculate the limit when x goes to plus infinity or minus infinity for rational functions, the method is that you divide the numerator and denominator by the highest power of x in the denominator, and here the highest power of x in the denominator in this question is x cube. So you divide the numerator and denominator by x cube and then you use this limit. Okay, so that's how we calculate this. Let us see, for example, if I choose x to be positive, that means I'm trying to take limit x tends to plus infinity, then limit x tends to plus infinity on this function, and when x is positive then this modulus of x cube will be simply x cube, and uh, because the highest power in the denominator is x cube, so first you divide the numerator and denominator by x cube to write it as 1 minus 2 by x cube, and over here 1 plus 1 by x cube. Then when x grows large, these two terms will uh, grow to or it becomes 0, and so the limit value is 1. Okay, so limit as x tends to infinity on the function is 1. Okay, so if you compare with this, then you see that the b value is 1 here. So we believe that y is equal to b, means y is equal to 1 is a horizontal asymptote to the function curve in the plus infinity side, okay, to the right of the domain. Okay, and if I choose x goes to minus infinity, that means x values are negative. So when x values are negative, then limit x tends to minus infinity on this function. So when x are negative, then modulus x cube will be minus x cube, and then by method you take x cube, and in the denominator is the highest power, so you divide numerator and denominator by x cube first, and then if you take limit, then you see that the limit value is minus 1. Okay, so here again by definition, if limit value at minus infinity is b, then y is equal to b is a horizontal asymptote. Okay, so here limit value is minus 1, that means y is equal to minus 1 is a horizontal asymptote at the uh, towards the minus of infinity. Okay, so we can see this graphically also. If you plot this fx function, then this is the fx function by blue curve, and you can see that y is equal to 1 is a horizontal asymptote at plus infinity, and y is equal to minus 1 is a horizontal asymptote at uh, minus of infinity. Okay, so one more thing you can see here is that the curve crosses once the uh, horizontal asymptote, okay, here. Okay, so that means it is possible that the curve may cross its horizontal asymptotes. Okay, it is also possible that the curve may not cross the horizontal asymptote at all, but it is also possible that it crosses the horizontal asymptote at some point, and maybe at infinite number of points. Okay, okay, say I take one more example here. Say using the sandwich theorem, find the horizontal asymptotes of the curve fx is equal to 2 plus sine x by x. Okay, so in this case again we are interested to find the behavior as x grows too large in the plus direction or the minus direction. Okay, so that's where we can find the asymptotes. So we know that the sine of x function is sandwiched between the 0 and the modulus of 1 by x function, and because the limit on this second function is always 0, okay, so by sandwich theorem the limit on the sin x by x function when x goes to plus infinity or x goes to minus infinity must be 0, okay. So by sandwich theorem, because if fx is less than gx is less than hx, okay, and if fx and hx has the same limit, then then gx also has the same limit at that point. So that result we used here to show this. And so the limit when x goes to plus infinity and minus infinity on this fx, if you calculate, then because this is going to 0, this sum will go to 2, okay. So the limit x tends to plus minus infinity on this function fx is 2, okay. So uh, you can see that y is equal to 2 is a horizontal asymptote to the right and also to the left, okay. And if we plot this, then this y is equal to 2, this red line is a horizontal asymptote to the right and also to the left for this function fx, which is 2 plus sine x by x. And one of the interesting fact here is that this function crosses the asymptotes many times, okay. Okay. Uh, the next is the oblique or slant line asymptote, okay. So asymptotes which are not parallel to x-axis, but they are at some angle to the x-axis, okay. So a slant line. So these are in particularly there when this holds, okay. If the degree of the numerator of a rational function is 1 greater than the degree of the denominator, okay, the graph has a oblique or slant line asymptote, okay. So if you are given a rational function and the uh, numerator degree is 1 greater than the denominator degree, then you are going to have a slant line asymptote there. And then how to calculate this asymptote is that uh, you rewrite that function by dividing numerator by denominator to express it as a linear function plus a remainder, okay. And as x goes to plus infinity or minus infinity, because this remainder will go to 0, okay, then whatever is the linear part left, that linear part is your slant or oblique asymptote, okay. Let us see this by this example, that to find the oblique asymptotes of the graph this function, okay. So given this function, and in this function it's a rational function with the uh, degree of numerator 2 and degree of denominator 1, okay. So degree of numerator is 1 greater than the denominator. So we can rewrite this function as a linear function plus a remainder, okay. So if I divide x minus 3 by 2x minus 4, then I can find the quotient and remainder, and then I can rewrite this as a linear function plus a remainder, okay. So if I write this x square minus 3 by 2x minus 4, then this is the linear function x by 2 plus 1 plus this remainder, okay. So if you solve this right hand side, you will come back here on the left hand side, okay. So the method says that if this remainder goes to 0 as x becomes too large in plus direction or minus direction, that means x goes to plus infinity or minus infinity, then uh, this linear function y is equal to linear function, and linear function is x by 2 plus 1, okay. So y is equal to x by 2 plus 1 becomes the oblique asymptote, okay. So as x goes to plus infinity or minus infinity, this because this remainder uh, goes to 0, so making this function y is equal to x by 2 plus 1, or you write it as gx by x by 2 plus 1, this linear function becomes the asymptote of the curve or graph of fx, okay. So if I draw this fx function x square minus 3 over 2x minus 4, then these blue curves are the graph, and it has this slant asymptote, okay, which is equation y is equal to x by 2 plus 1, okay. So to find this line, what you have to do is write this as a linear function plus remainder, and if remainder goes to 0, then this linear function is this slant line. Okay, so which is the oblique or slant asymptote to the curve. Okay, and in this case, both at x goes to plus infinity or minus infinity, this is the same line. Okay, so this same line also at the plus infinity and also on the minus infinity. Okay. Okay, in this particular question, there is also a vertical asymptote. So we'll talk about this in a few minutes once we define uh, the infinite limits at finite points. Okay, so that's what exactly we are going to do, defining infinite limits. Okay, so for infinite limits, the function grows arbitrarily large, either in the positive direction or negative direction away from 0. Okay, for finite value of x. Okay, so we can define it that we say that fx approaches infinity as x approaches c, and write that limit x goes to c, the function uh, goes to plus infinity if for every positive real number b there exists a corresponding delta positive, such that for all x which are within the delta distance from c, the function values grow much faster than b. Okay, so for every real positive b, the function is still greater than that b. Okay, so you choose any large b, the function values are still more larger than that. Okay, so function grows to plus infinity. Okay, for all x inside the delta interval. Okay, similarly, we can define that the function approaches minus infinity as x approaches c, and write that limit of function as x approaches c is minus infinity if for every negative real number minus b there exists a corresponding delta positive, such that for every x which lies in the delta interval from c, the function values are much smaller than this minus b value. Okay, so you choose any negative real number, the function grows in the negative direction much bigger than this negative number. Okay, uh, where for all x in this delta interval. Okay, so if this is true, then we say that limit x tends to c f(x) is minus of infinity. Say for example, show that limit x tends to 0 on 1 by x square is plus infinity. Okay, so given a b positive, we want to find a delta positive, such that for every x which lies within a delta distance from origin, because we're trying to calculate limit at origin. Okay, so for every x which lies within a delta distance from origin, the function grows faster than this b. Okay, so the function values are still greater than this b for every b you can choose. Okay, so again, if you remember, the method still remains same, that you have to solve this inequality first and then correspondingly try and find this delta. Okay, so if I solve this, then this holds if and only if x square is less than 1 by b. Okay, so x is less than 1 by root b, and if you compare, then you can see what delta is. Okay, so if you compare these two, then you can choose delta to be 1 by root b or any smaller positive number than this. Okay, and by choosing this, then these two results will simultaneously hold, and that means these two will simultaneously hold, and which immediately implies that limit x tends to 0 1 by x square is plus infinity. Okay, so uh, by choosing delta to be 1 by root b, that means for all x whose distance from delta from origin is within delta, implies that the function grows much faster than any chosen b value. Okay, so function goes to plus infinity. Okay, and so we can write that limit x tends to 0 1 by x square is plus infinity. Okay, so graphically it says that you choose any number b, doesn't matter how high you choose this, the function grows much faster or then this value within this delta distance. Okay, for every x. Okay, now we talk about the vertical asymptotes, and just like horizontal asymptotes means the lines parallel to x-axis, vertical asymptotes means finding lines uh, parallel to y-axis. Okay, so vertical lines, and we know that the equation of vertical line is like x is equal to a. So a line x is equal to a is a vertical asymptote of the graph of a function y is equal to fx if either the function grows too large to plus infinity or minus infinity when we approach x, when we approach point a from the positive side, or the function grows too large to plus infinity or minus infinity when we approach a from the negative side. Okay, so limit of function when we approach a from plus side, okay, from the right of a, or the limit of function when we approach a from the left of a, if they grow too large on the positive side or negative side. Okay, then we say that the point x is equal to a is a vertical asymptote of the function y is equal to fx. Okay, so to calculate this you need to check uh, either of these, and if you get any uh, where that the function grows too large, then immediately you can say that x is equal to a is a vertical asymptote. Okay, so for example, say we have to find the horizontal as well as vertical asymptotes to this curve y is equal to x plus 3 by x plus 2. Okay, so now we know that we calculate horizontal asymptotes when x becomes too large either in plus direction or minus direction. That means the behavior when x goes to plus infinity or minus infinity, and vertical asymptotes when function grows to plus infinity or minus infinity for any finite x values. Okay, so first we'll calculate horizontal asymptotes. Okay, so that means what happens when x goes to plus infinity or minus infinity, and it's a rational function, and to solve rational function what we do is we see what is the highest degree in the denominator. Here it is x, so divide numerator and denominator by x, so we can write it as 1 plus 3 by x divided by 1 plus 2 by x, and then when x goes to plus infinity the value of limit is 1, when x goes to minus infinity the value's limit is 1, so the curve tends to y tends to 1. Okay, so immediately we can say that uh, y is equal to 1 is a horizontal asymptote at both ends. Okay, and now for vertical asymptotes we have to find values which makes the function grow larger, and usually you can see that the whenever the denominator will tend to 0 then the function will grow large and large. Okay, so x is equal to minus 2 is the point where denominator goes to 0. So we'll check what happens if we approach this point minus 2 from the left, and what happens when we approach this minus 2 from the right. Okay, so the limit when we approach minus 2 point from the left for the x values which are smaller than minus 2. Okay, so on this function when we apply, then we can substitute x as minus 2 minus h. Okay, so numbers which are smaller than minus 2 can be written as minus 2 minus h for h positive. So if you substitute x as minus 2 minus h, then numerator will become 1 minus h and it will become minus h, and then only limit h tends to 0. So when goes to 0, then 1 minus h will be positive. For h going to 0 it will be very small, and this number will be negative, so uh, this will be 1 by very small number, so it goes to minus of infinity. Okay, similarly when x approaches minus 2 from plus side, then in that case we can choose x to be minus 2 plus h. Okay, so if I put x to be minus 2 plus h, then numerator will become 1 plus h and denominator will become simply plus h, and when h goes to 0 then numerator is 1 and denominator goes to 0, so it will go to plus of infinity. Okay, so what we have is that x is equal to minus 2 is uh, a vertical asymptote. Okay, and why we calculated the left and right, because it tells us that what happens to the function curve when function curve come from the left side, and what happens to it to the right side. Okay, so when x goes to minus 2 from left side, the function values are going to minus infinity, so curve is going downward to minus infinity near x is equal to minus 2. And when we approach from the right, then the function values are growing to plus infinity near the minus 2 point. Okay, so if you plot this, then there is a horizontal asymptote y is equal to 1. Okay, and there is a vertical asymptote x is equal to minus 2. And by these limits you can see that when you approach minus 2 from the left side, then the curve goes to minus of infinity, and if you approach minus 2 from the right side, then the curve goes to plus of infinity, which is this limit values. Okay, okay, now I take one more example here. Say find the horizontal and vertical asymptotes of the curve y is equal to minus 8 over x square minus 4. Okay, so here in this case you can see that the function is a even function symmetric about y-axis. Okay, so whatever happens to the positive x direction, the same things will happen in the negative of x directions. Okay, so this is our first note, that y is a even function of x, that is graph is symmetric about the y-axis. Okay, so for the horizontal asymptotes, we will first check what happens when x goes to plus infinity or minus infinity. Okay, when x goes to plus infinity, y goes to 0. Okay, and by symmetry, obviously when x goes to minus infinity, y goes to 0, because it is symmetric about y-axis. Okay, so this the b value is 0, so y is equal to 0, or x-axis is the horizontal asymptote of the graph of this function to the right, and by symmetry also to the left. Okay, so by symmetry y equal to 0 is also a horizontal asymptote to the left. Okay. Now the second question is that what are the vertical asymptotes? Okay, so what points makes the y grow larger? Okay, usually the points which makes the denominator too small. So if you solve, then you will see that x is equal to 2 and minus 2, the denominator tends to 0. Okay, so let us check this behavior as x goes to plus 2 or x goes to minus 2. And so when limit x tends to 2 from the plus side, okay, then the limit x tends to 2 on the plus side for this function. That means we can, if I put x as 2 plus h, okay, for h going to 0, we can check then the limit, that limit h goes to 0, put x as 2 plus h and solve the denominator, then we'll have this. So when h goes to 0, h is very very small, then this will become infinity, and there is a negative sign here, so this overall result is minus of infinity. Okay, so when you approach the point 2 from the right side, then the function value goes to minus of infinity. Okay, similarly if I check the limit x goes to 2 from the negative side, then I can substitute x as 2 minus h. Okay, x as 2 minus h, and then check limit h goes to 0. So if I open 2 minus h square, then 4 will cancel out and denominator will be h square minus 2h. Okay, now when h goes to 0, h is very very small, then the h square terms will be less than 2h terms. Okay, so this denominator values will be negative, and so this minus sign will cancel out with the minus sign in the denominator, and it will give us a plus infinity value. Okay, so when you approach 2 from the negative side, the function grows to plus infinity. Okay, okay, and because the graph is symmetric about y-axis, so whatever is happening at 2, the symmetrically it will happen at -2. Okay, so if you approach 2 from plus side, from the right hand side, then it goes to minus infinity. So that means if I approach -2 from the left hand side, it will grow to minus infinity. Okay, and similarly if I'm approaching 2 from the negative side to plus infinity, then -2 from the positive side will go to plus infinity. Okay, so x is equal to 2 is the vertical asymptote from right as well as left, and it is all, then x is equal to -2 is also a vertical asymptote from the left as well as from the right. Okay, so we have one horizontal asymptote y0, and we have two vertical asymptotes, x is equal to 2 and x is equal to -2. So if we plot this function y, okay, by blue curve, then you see that y0 is a horizontal asymptote. The curve uh, gets closer to the x-axis as x goes to plus infinity or minus infinity, and at x is equal to 2 is a vertical asymptote with when we approach 2 from the plus side, the function goes to minus infinity, and if we go to from the negative side, then function grows to plus infinity. And due to even function symmetric about y-axis, the curve on the right and the curve on the left are same. Okay, so this is how you calculate your asymptotes, horizontal as well as vertical. Or you can also calculate slant asymptotes if you have a rational function with the degree of numerator 1 greater than the degree of denominator. Okay, so I now we'll close this with the few examples where you can think about these statements, whether they are true or not. If they are true, then say why they are true, and if false, then give a counter example that confirms that yes, they are false. Okay, so one statement says that if limit x tends to c, fx exists. Okay, so if limit on function fx exists as x approaches c, but the limit on gx do not exist when x approaches c, then the limit on sum at c does not exist. Okay, so that's one question. Second is that if both limits x approaching c fx and limit x approaching c gx do not exist, okay, then the limit on sum also does not exist. Okay, so that's second. Third is that if a function is continuous at x, then so is the modulus of function. Okay, and the fourth result is that if modulus of function is continuous at point c, then so is the function itself. Okay, so these are the four statements, and we have to see whether the statements are true, or if they are not, then we have to give a counter example to show that they are false. Okay, so here the first statement is true. Okay, if one limit exists and second do not exist, then limit on sum do not exist. This statement is true. Okay, the second statement uh, is a false statement, because even when the two limits do not exist, then some limit may exist. Okay, so I will give a counter example for this. Okay, uh, if function is continuous, then so is modulus. This statement is also true. And the last statement is that if modulus is continuous, then so is the function at that point. Okay, so this statement is false, so I will also give a one counter example for d. Okay, so first we talk about this first statement, and this statement is true. Okay, the reason is simple, that we know that if the uh, you know the limit on one function exists and the limit on second function exists, then by the limit rules we know that the limits on sum also exist. Okay, so if I assume that the limit on sum exists, okay, then this is a limit on one function, say hx. This is a limit on fx exist. Okay, so let this limit exist and this sum limit also exist. Okay, so by difference rule, the limit on this minus this must also exist, but the limit on fx plus gx minus fx is actually the limit on gx, which do not exist. Okay, and our assumption that this limit exists is false. Okay, because if this limit exists, then the difference of this and this must also exist. Okay, so by difference rule, so because this does not exist, so this should also not exist. Okay, so this statement is true. Okay, the second statement was that if both do not exist, then the limit on sum also do not exist. This statement is false because we have counter examples for this, that say for example, if you have a function which has a uh, jump discontinuity at origin, so limit at origin do not exist. Okay, and similarly if you have a gx function which is also has a jump discontinuity at origin, and limit at origin will not exist for this function, such that the sum of the two function is zero. Okay, so sum function is a zero function. Okay, and so this function is continuous at origin. Okay, so here's the plot for these three. Okay, this is a fx function which is not continuous at origin, gx function not continuous at origin, but the sum function is continuous at origin. Okay, so the statement that if the limit on fx do not exist and limit on gx do not exist implies limit on sum do not exist, this statement is not true. Okay. The third question was that if function is continuous at x, then so is modulus of the function. Okay, so this statement is true. The idea is that we have to show that this modulus function is continuous at x. Okay, and to prove continuity we have to prove that uh, the modulus of function minus the value at the point a, this difference is less than epsilon, and there is an inequality which says that the modulus of this is less than modulus of this. Okay, and because function fx is continuous, then this function difference from f of a is less than epsilon. Okay, by continuity definition. Okay, so you can also prove this holds using this holds. Okay, so that's just a hint. You can solve this and find or prove that modulus of f is continuous when f is continuous. The converse is not true. If modulus is continuous at a point, does not mean that the function is continuous at that point. Okay, so converse is not true. Okay, so counter example is this, that uh, if you have a jump discontinuity at origin, uh, okay, of this form, then if you calculate the modulus of this function, then modulus of this function is 1, and this function is continuous for every x. Okay, so this function is also continuous at origin, but the function itself is not continuous at origin. Okay, so modulus function is continuous at origin, but function is not continuous at origin. Okay, so if modulus continuous is function is continuous at any point, then it does not imply that function is also continuous at that point. Okay, so this statement is false. Okay, so I close this topic here, and in the next lecture we'll talk about derivative of a function of a single variable. Okay, till then, have a good day.